Hello everyone, my name is Iman. I am an undergraduate student in chemical engineering at Polytechnique Montréal, and I had the opportunity this summer of working with the recycling team on a project regarding the production and recycling of metals. I was mainly focused on steel, which is why I am going to complete the first part of this FactSage workshop by presenting you a simulation of steel recycling. More precisely, I will do a stainless steel remelting through the electric arc furnace. So I'll start by giving you some context on steel recycling in the industry. So new steel products usually contain about 30% of recycled steel, plus approximately 630 million tons of scrap is recycled every year, which saves around 950 million tons of carbon dioxide that would be emitted by steel productions. So now let's talk about the scrap itself. Steel scraps can be sorted into three categories. We first have the home scrap and the new scrap, which are kind of similar. Both of them won't leave the metal production or the manufacturing, and this makes it a lot easier to recycle them since the chemical composition is known. Then there is the old scrap, also called obsolete scrap. There are the post-consumers products that have reached their end product life. It would be a lot harder to recycle them since there will most likely be contamination throughout the use of the products, and that requires more treatments. So here are some contaminants usually found in old steel scrap. We have copper from the copper wires, zinc from galvanized steel, lead from batteries, and the rest from oils. So scrap can be introduced in the two pyrometallurgical ways of steel production. It can be added to the basic oxygen furnace as a coolant, since most of the reactions occurring in that furnace are exothermic. There is around 25 to 35% of scrap added. The other way to recycle steel scrap is through the electric arc furnace that can have up to 100% of scrap that will be remelted into liquid steel. There will be times where contaminants will need to be diluted, which is why we would sometimes need to add direct reduced iron from the direct reduction furnace. So the steel production right now is around 72% from the basic oxygen furnace and 28% from the electric arc furnace. So what I've put in blue here is what we are going to simulate today. So I will talk a bit more now on the electric arc furnace itself. So here's an overview of the equipment. So the scrap will get charged in the bottom of the furnace, and the graphite electrodes, represented in black, will go down until they reach the scrap. They will create an electric arc that's represented in red that will increase the temperature until around 1600 degrees. Then oxygen is blown into the liquid metal to oxidize some of the impurities of the scrap, which, along with the flux added, will create a slag phase at the surface of the metal because of the density difference between the two phases. Now we will see that there are elements that we don't want to oxidize, such as chromium and iron, but they will get oxidized anyway, and that is why we are blowing carbon into the slag phase to recover some elements that we don't want to lose. We also have our gas phase, which is mainly composed of CO, CO2, and air. So here's the mass and energy balance, which is the real life data that we are going to refer ourselves to as we go on with the simulations. So the purpose of this presentation is to simulate the equipment and compare the data that we are going to get with FactSage. So here's the outline of the different FactSage calculations that we are going to do today for the next 20 minutes or so. We will first focus on the energy balance of the recycling of stainless steel. We will determine the initial state of the scrap and the heat balance of both phases. Next, we will focus more on mass balance of the recycling, so what happens when we will blow the oxygen and carbon in both the liquid metal and slag respectively. And we will then finish this presentation by doing a copper contaminated steel scrap recycling that will require direct reduced iron addition for dilution. So let's begin with the energy balance simulations. So first we need to select the databases that we need. So opening a new Equilib module, you can click on data search, and we are selecting three databases for the simulations. We first have FactPS that contains different compounds like our flux and also the gas that will be formed. Next, we have Fs steel, which we can find multiple iron-based phases like our liquid metal, our austenite, our ferrite, etc. And finally, we'll select Ft oxide, which contains our slag phase made of different oxides. So let's start by finding the initial state of the steel scrap. So in a new equilibrium module, I entered the composition of a 316L stainless steel, and this calculation will be done for 1 kilogram. So as you can see, there's almost 19% of chromium, which is an expensive alloying element. So the challenge with recycling this scrap is to avoid chromium oxidation into the slag when we inject oxygen. Since we are not calculating any energy demand, we don't have to activate the initial conditions. So the initial state of the scrap will make a difference in the energy balance. So to see all the phases present in the steel scrap, we will assume an equilibrium at a temperature of 500 degrees. So our hypothesis here is that the scrap's internal structure is described by the phases at equilibrium at 500 degrees. So we can activate all of our phases and impose a temperature of 500 and then hit on calculate. So here's the results page we get. So at 500 degrees, we have 7 phases at equilibrium. So out of a basis of 1,000 grams, we can see that austenite and ferrite are the most present. So now we need to save all of these streams by going into output, stream file, save stream file, and then save solutions. And my first solution was FCC, so I'm selecting this one, but we have to save all 7 of them for our next simulation. So now that we have all of our phases saved, we need to cool our streams since the scrap will enter the electric arc furnace at a temperature of 25 degrees. So I'm going to show you one example with the FCC phase, which is austenite. So opening a new equilibrium module, you're going to go in Edit, Mixtures and Stream, import a stream, and then choose the stream that you saved. Mine was FCC at 500. And just a reminder, the 100% here represents the mass of the phase you saved. So in our case, we had approximately 365 grams of FCC. So that's the amount that got imported. Then you click on Next. So now we don't want any change in the chemistry of the phase or any transition of phases. So we will only select the phase we imported. So you can right-click on the FCC and choose single phase. That way we are going to get the same phase with the same chemistry, just at a different temperature. You can impose a temperature of 25 and then hit on calculate. So as predicted, we only have one phase at 25 degrees, which will also be saved because this is what is going to enter our electric arc furnace. So when that's done for the 7 phases, we can move on to our third simulation, which is the heat balance. So you can import all of our streams at 25 degrees. I also added oxygen and flux that we are going to use a little bit later. But the important thing here is that we need to activate our initial conditions since we are calculating an energy requirement. So we can select all of our phases, so the gases, the pure solids, and the solutions. We are having beta as 25 since we have a flux of 50 grams, and we had 2 flux components, SiO2 and CaCO3. We don't have the oxygen yet because we're only calculating the heat balance of the formation of the metal and the slag phase. You can put a temperature of 1600 and then hit on calculate. So at the bottom of the results page, you have all of the state properties of this calculation, and we find a delta H that has been converted from kilowatt-hour per kilograms to kilowatt-hour per tons. And if you calculate the ratio of these two values, we would have a furnace efficiency of 0.76. So now let's move on to the mass balance of the electric arc furnace. So as I showed you in the beginning of the presentation, we are going to inject oxygen into the liquid metal to oxidize the different impurities. So in the mass balance, we know that we need approximately 50 grams of oxygen. So to see the different oxidation reactions, we will make alpha vary from 0 to 50. We still have our flux at B equals to 25 and our temperature of 1600. you can select all of your phases, and we will see that the element in blue will most likely get oxidized while the element in purple will not. So to have a better visual, you can go in output and then plot. Uh, and the axes we choose are the weight percent of the different elements in our liquid metal as a function of alpha, which is our oxygen addition. So we can see how the chromium in the metal reduces as we add oxygen. Nickel and molybdenum did not oxidize. So as we can see, the bottom of the graph is a little bit packed. So what we can do is go back to the plot window and change our maximum value. So first I had 20, now I'm going to put 1, which gives me this graph, which is a lot more clear. We can see the oxidation of manganese, of carbon, and silicium. We can also see that the carbon has reached its specification of a stainless steel composition of 0.2%. The second graph we can do is to do the mass of the different phases in equilibrium as a function of oxygen blowing. So I'll keep the same variable in the x-axis. I'll just change the y-axis and put the mass of the phases. So as predicted, the liquid metal will increase, and we have an increase in corundum and spinel phase, which represents the transfer of the chromium and the iron atoms. So if you're wondering why we have a slag phase at A is equal to 0, that's because we had the flux present. So that already itself produced a slag phase. Now we can move on to the next simulation where we will inject carbon into the slag phase to recover the iron and the chromium that we lost earlier. So what I've done is I saved all of my phases at A is equal to 50 from my last simulation. So these three phases at A equals to 50. So when all of my oxygen has been blown, and I imported them in a new equilibrium module and added solid carbon at 25 degrees with an alpha parameter. So referring to the mass balance again, we need 5 to 15 grams of coal for 1 kilogram of recycled steel, which means that we can make alpha vary from 0 to 15 to see again the evolution of the reductions of the different oxides. So we're going to do kind of the same analysis we did with the oxygen. We still have all of our phases activated and our temperature of 1600. You can hit on calculate. And what I've done is I plotted the exact same graph we did earlier with the oxygen. So I selected the different phases at equilibrium as a function of carbon injection. The important thing to analyze here is the decrease in the corundum phase, as well as the increase in the liquid metal phase, which represents the chromium recovery. But another interesting thing we can do is have numbers to represent that recovery. So when you go on your results window at A is equal to 15, which is all of our carbon injected, when you scroll down a little bit until you reach your first liquid phase, in my case, it's the slag, you can scroll down a little bit more and you have the mass of the different elements in that specific phase. So for instance, we can see that there's around 57 grams of chromium in my slag phase. So I made a table with all of my phases and their chromium amounts. And I also went back to the last simulation and find the chromium amount in the liquid metal after we added all of the oxygen, since we didn't include the liquid phase in that simulation. So now that we have all of this information, I added the chromium amounts in both the liquid metals, and I divided it by the total chromium amount in all of my phases, and that gives me a recovery of 56.78%. That number can definitely be higher considering that it is an expensive alloying element, so we want to recover as much of it as we can. But this number could increase if we would increase the amount of carbon injected. Another thing we can do is to refer back to our mass balance for our outputs. So in total, adding the mass of the liquid metals in the last two simulations, we have 907.311 grams of liquid steel versus 1,000 grams, which can be explained by the low chromium recovery as well as the oxidation of impurities. Then the slag phase respects the data interval with 128.70 grams. So the last example I'm going to show you is another challenge that the industry deals with, which is the contamination. So here we will dilute a copper contaminated stainless steel with direct reduced iron coming from the direct reduction furnace, since copper will not oxidize when we will blow our oxygen. So we will see that FactSage can actually calculate the exact amount we need to do our dilution. So we're going to create a new equilibrium module with a direct reduced iron containing 96% of iron and 4% of carbon. So we are going to make the same assumption that the internal structure of the DRI is represented as the equilibrium phases at 500 degrees. So we can still select all of our phases, but we are going to right click on the pure solids. And we are going to do that because the carbon containing phase in DRI is mostly cemented. Not 100%, but in this simulation, we will assume that it's only cemented. So we are going to right click on both the carbon allotropes and make it dormant. A dormant phase, which means that this phase will not be considered in our phase assemblage. So then doing the calculation at 500, we have both of our phases. It is important to note the masses of these phases because we are going to need those values later. So we can save both our streams and then do the stream cooling. I will go over that simulation a little bit faster since we already done stream cooling in the beginning of the presentation. So you import your stream at 500, you only select your solution, impose a temperature of 25, and then save your streams at 25 degrees. Now we are ready for our last simulation, which is the dilution itself. So the mass balance is the same as the oxidation. We have our scrap, we have our oxygen, we have our flux, but this time we are adding 2.5 grams of copper and our DRI, along with the alpha parameter. And note that the numbers that I put there are the masses of both the phases. I just multiplied it by 10 since we are we're doing calculations out of a basis of 1 kilogram. Now, according to the AESTM norms of ferrous scrap, the composition of copper should not go above 0.2%. So a very interesting thing we can do is right-click on our liquid metal and select composition target. We can select species composition. Our goal is to have the composition of copper, so we'll select copper here, and at the bottom, we can choose the composition target that we want. So in this case, it's 0.2%. So you can click on OK, and FactSage will actually calculate alpha such as the copper composition of the metal will not go above 0.2%. So we get an alpha of 0.137, which gives us this mass of DRI, 137.047, and that gives us a percentage of recycling of 87.9%. So to conclude, we did a simulation of the electric arc furnace. So we did the remelting of a stainless steel with oxygen and carbon injection. Then we treated a case of old scrap with copper contamination and used direct reduced iron to do a dilution. Thank you guys so much for your attention. If you have any questions or comments, I can take them now.